Thank you so much for having us. I am SUCHI SARIA. I'm a professor at Hopkins. I have worked extensively on the intersection of causality and machine learning, various aspects of it. But today we're going to talk about what I think is a super exciting, important, and timely topic. And then joining me will be Adarsh Subaswamy. Adarsh, you want to say hi?
Hi, yeah, I'm Adarsh. I'm a fourth year PhD student, fifth year PhD student working with SUCHI on these topics.
But he's much wise beyond his age. So let's just dive right in. So I think one thing that's been really interesting and I would say a little difficult is, 3, 4, 5, 6 years ago, machine learning researchers, that community was actually a pretty small community, which meant it was extremely easy for, as a field, we progress really fast as new ideas come to light. We come up with ideas for fixing it. And we were able to get by communicating amongst ourselves really, really fast. And one thing that's changed now in the last 4 to 5 years is as the field's expanded dramatically, and most importantly, as the application of machine learning is moving across many, many domains: education, healthcare, uh, criminal reform, transportation, and areas that have very practical relevance in our life. It's not just about the technical aspects of building machine learning models and improving model training. We have to now start thinking a lot more seriously about the downstream consequences of our models as we deploy them, and thinking about how model training impacts how reliably the model behaves, whether it behaves in unanticipated ways, whether it leads to failure modes that can have very dramatically bad consequences. And that's really what's that's motivating this whole line of research in machine learning, which is how do we improve model reliability and reliability of machine learning pipelines overall. And so just to start off as a little imagery, I think in the last, I feel like when we go to meetings outside of machine learning, there's just so much excitement for the field. And a lot of what I feel practitioners, their point of view is machine learning is the electricity, right? AI is the new electricity, as people call it. And that it's going to transform every industry, every sector. And it's this beautiful, elegant bridge that's just going to work, except as someone who participates in the making of it and the building of it and the development of it, as researchers, we know that there are just so many nooks and crannies you have to navigate in order to be able to build something that truly works. And part of it has to do with the shift in historically what was entirely on evaluating performance using AUCs on 1 to 2 fixed data sets. But now going forward, I think as we've moved into real world deployments, there's many more forms of interactions with our models. For example, even something that's brought in a lot of attention in the last couple of years is like, once we have a data set, we can build a model and we can make all sorts of claims. But but should that model have even been built to begin with? Or that you're making a claim with your model that can help you do this and that, like help you do amazing recruiting, but actually the model claims are completely false. So there's harms from misuse. There's consequences, more subtle and technical consequences, like as the model moves from your training data set to a deployment data set, how does that then impact model performance? And then just more broadly, what are the different error modes as it moves into the real world? And those are all things we have to think a lot harder about. And I'll let me give you like examples even that have surfaced as a starting point, and then there are many. So it seems like you can't see. Are you not able to see my slides as I'm progressing?
We can see your slides. We can see the screen.
Oh, you can. Okay, because others seem to think that you could only see my title slide. Okay, so I'm going to assume people can see my slides, but if you can't see my slide, please write in the chat box and then we'll fix it.
It's good now.
Okay, perfect. So the slides will all be posted, so hopefully you'll get a chance to see it if you haven't seen it. But effectively, just very quickly, I went through kind of where the challenges are and now driving into a few examples. So this was an example of a study that was done where they looked at chest X-ray images, and what they found was they trained a machine learning predictor to identify whether the chest X-ray, the patient from whom the image was taken, whether this patient had pneumonia or not. Pneumonia is a disease or a complication. And what they found was the model worked really, really well when they worked on, and they applied it to one hospital. They took the data, they did your standard trained test, and the model worked exceptionally well when you looked at the test data. Now, when you went from one hospital to the second hospital and the third hospital, what they found was the model performance deteriorated. And surprisingly, the model performance was fine when you went from the first to the second hospital, but then suddenly on the third hospital, it deteriorated. So that creates this very strange thing, right? Because as developers, how many data sets do we test on to even believe that a model is working? Like maybe it's working on the first and the second and the third, and is it suddenly going to just misbehave on the fourth? And as editors and reviewers and people who are trying to use these to deploy, it's scary from their standpoint if they can't even understand like when you have guarantees and when you don't. But we will come back to this example. Another example, again, very critical. This is one in LA. This was crime department, police department that was using data to identify where there were going to be, to predict which neighborhoods we would see crime. And then based on, and then they would send their troops there. And ideally, what they found was they were able to catch more criminals. But one of the very bad unintended consequences was that the more they went to certain neighborhoods, the more they were catching crime there, the more data they were collecting in those neighborhoods, the more the naive way of training models kept reinforcing this idea that maybe that's where all the crime is. And so you had sort of this feedback loop. So you had this feedback loop that was reinforcing that the model couldn't be robust to. Rodrigo, do we need to pause and take a question?
No, but actually the slide's still on the same one with the X-rays. I don't know if you have changed it already.
I did change it.
Well, it stayed on the X-rays for some reason. Strange.
Is it different now?
No, it's still the same with the X-rays.
So that's odd because I'm sharing my screen. How about now? Can you see it now?
Well, now we see that, so it's not full screen, but we can see everything. So maybe we can stay as that.
Yeah, that sounds like a good practical plan. I can just expand it. Is there a way to expand fit in window maybe? Yep, there you go. All right, so this is the slide I was on. I was talking about predictive policing and talking about essentially how effectively by using machine learning to predict where the crime was, they were sending troops there to collect more data. The more data we were collecting in certain neighborhoods where we were discovering crimes, the more that data was now being used for learning and updating our learning algorithm. And it was reinforcing this bias that crimes exist in these neighborhoods where they're policing more. Does that make sense? Here's a third example. This is a very popular example people have spoken about, where on the x-axis here in this image, there's a panda. The machine learning method performs really well in identifying this as a panda. We add a little bit of noise to this very specific way, and out comes a new image, which to humans, it's imperceptible. It looks like the original image, and we would say, of course, this is a panda. But for a machine, again, there are ways in which if the machine is not trained correctly, and if the model is the model is sensitive to these kinds of what are called model blind spots, you can end up in the situation where the model thinks this is actually a gibbon and not a panda. And again, another example of like behaving in unexpected ways. Couple more examples. So here's an example where this is actually a really interesting practical example with lots and lots of applications. So this is this is data we were looking at in a hospital, where we're looking to look at the labs data and the vitals data and all kinds of data that are collected on patients to be able to predict whether the patient will be at risk for a particular complication. And turns out, over time, as clinical guidelines change, physicians tend to practice differently. And so in this one very specific example, there was a national guideline that changed. And as that guideline changed, people started changing the ordering pattern. And as you change your ordering pattern, your model's performance completely drifted and deteriorated. So there's a machine learning diagnostic model that you think was performing really, really well. As the ordering pattern changed, it started missing patients altogether, which can be very dangerous. Two more quick examples. So this is one where where face detection, face recognition, this is being used everywhere in practical examples, in surveillance at airports, on the internet, in all sorts of e-commerce retail applications, where using images like on Facebook, you automatically identify whether the person is a human or not. And essentially, this paper showed that there was a very big discrepancy in performance of our state-of-the-art face recognition algorithms on blacks versus white and females versus males. Again, all scenarios where we have great intentions when we are developing these models, testing and evaluating these models, but historically our need for testing, developing and evaluating were entirely based on, I have 1 or 2 data sets, I can show you performance, but now we have to be far more comprehensive. And we have to think much harder about, where the lack of performance or variability or inconsistency in performance can hurt the downstream application and lead to harmful societal impacts. Last example, which is one that was, I think, very quite nonsensical and ridiculous. There was a application where people claim that you could take an image of a person's face and from that guess what their career it is that they would be suited to. So are you a high IQ person or a low IQ person? And therefore, are you going to be a researcher versus a professional poker player versus a terrorist? And as you can imagine, there are enormous consequences here in terms of what the issues are. So first of all, imagine if you had a bad and poorly trained algorithm and you were using it for recruiting to rule out candidates, that would be terrible. But second of all, more fundamentally, this is an example of an algorithm where all it's learning is associations from data. It's just trying to mimic today what types of people look like that hold a certain job. And as we well know, there's so much bias in recruiting and so much bias on who gets selected for what job, but also who ends up going to a job, right? Like there's, and so effectively what it would be doing is learning the bias that exists today and just kind of reinforcing it, right? So to put it all in one big framework, I gave you 6, 7 examples, but at a high level, very often these issues and errors kind of fall into these 4-ish categories. So the first one is like bad or inadequate data. So you're just answering questions that cannot be answered reliably using the data we have access to today. And so the example we talked about with faceception, and the example we talk about with face recognition, where you don't have an adequate sampling of blacks and black females in your data set, will lead you to scenarios where your model itself can't be high quality. Now, you can fix that by trying to change your data. You can try to fix that by changing the question you're asking, because maybe you're asking a question that's not feasible to answer, but that's sort of one category. And a lot of egregious examples fall into that first category. Now, the second category is model training associated. So this is an example where the model you're learning is just misspecified. You have the right question, but you're learning the wrong model. Like you need different objective functions that are more robust to certain kind of perturbations, or your learning algorithm itself, or your training, your optimization procedure itself is going to lead to local optima where there will be blind spots. And so That's more technical, it's more nuanced. I think in a variety of different model scenarios, we're learning about when they work well and don't work well, and then what are ways in which we can regularize to improve quality of these models. The third type is very subtle, happens all the time, and one I gave you an example of, which is where the algorithm is working great. In that pneumonia example, the chest x-ray image, it works great, one hospital, second hospital. Turns out when you went to the third hospital, you just had a different equipment. Or in the example I gave you where we were trying to predict this complication and physicians changed their ordering practice pattern. Or the example of predictive policing. Basically, your one way or the other, the environment or the input data are shifting, and that's leading your model. And if you don't train models that are robust to these, you'll end up in situations where the model behaves in ways you don't expect it to. And this issue is pervasive. The fourth and last example is kind of more what I would consider the kind of intersection of like model machine learning, but really also machine learning and communication, like how we describe and summarize what are our models actually learning so that the end users don't end up extrapolating more than it is or end up misusing it. And so this has notions of, can we come up with like report cards, right? Like cards for summarizing model performance. When does the model perform well and not perform well? Which has really, and the interesting things that are parallel from all sorts of other fields where we can learn things. So very often when we're building machine learning models and we're deploying them, we're really trying to impact some real world thing. Like the goal of our models is to influence some kind of behavior, right? You're getting people to change the way they're making some decisions, or you're getting them to, maybe order some things that they weren't ordering, or diagnose patients differently, or change the way we're doing policing, or change the way we're determining, who should or shouldn't be, get extra attention when we're talking about, policing, criminal justice and analyzing cases of victims. So what I'm talking about here is like in any one of these scenarios in other fields, like in medicine, there's been a huge history of studying algorithms and running trials and prospective trials where we think about performance and efficacy, and we think about efficacy in the context of an application and an end use case. And we need to be thinking about our algorithms and our pipelines in the same way. How do we measure efficacy of these solution sets as we deploy them? The second area where I think there's a lot of ideas for us to learn from is civil engineering and like nuclear engineering, where effectively, the consequences of getting things wrong are very, very high. So they have a huge, very mature framework around this notion of reliability and how do you engineer for reliability, and what are principles to adopt and frameworks for being able to engineer for reliability. So based on that, I'm kind of extracting at a very high level, I think, what this means for machine learning. And then I will take a piece of it today and then we'll drive deeper into that, which is, so 3 key areas. First is, how do we even become more proactive rather than reactive? So proactive means when we're going to build and deploy a system, a learning algorithm to support an application, can we more proactively think about failure modes? Can we build learning algorithms that are less, that are more robust to against these failure modes? So here it's all about moving from our current methods of learning to moving to what I would call, reliable learning or robust learning methods, where the resulting models that we're getting are just more failure proofed. And thinking about, and much of today's talk and today and the rest of the tutorial will focus on that. But just to cover briefly, there are other aspects of it. So it's not just about build your learning algorithm, make it very accurate, and then stop there. The reality is if you're going to build it and deploy it, something in the world is going to shift and change. Maybe you were able to learn and you tried the hardest you could, but in the real world, issues will come up. So that leads into the second bullet point, which is how do we monitor these on the fly? Like, how do we detect likely mistakes? Can we identify when something is becoming unstable and needs to be retrained? Can we identify when something isn't working well? And then third is, how do we now go from identifying when things aren't working well and ways to detect this to this notion of maintenance, right? And maintenance sounds like a boring word, but really it's what we call some notion of like continual learning, but continual not in the sense that we have to be learning continuously every second, but more as a version of, as we get more data, as we learn about more complex populations, as there are drifts in the environment, how do we adapt? How do we adapt the resulting models to these scenarios? So that's sort of roughly like 3 key areas, borrowing principles from reliability engineering, where from other fields, where if we were to think in this way, there's enormous opportunity for work in each of these bucket areas. And in 2019, we gave a little tutorial on this, and we dive into each of these 3 areas in much more detail. Obviously, it's very expansive, but so there's only so much justice we could do. But today, we'll actually focus on only the first, which is there's been an enormous amount of progress in the last few years in terms of thinking about how do we build models that are robust. And so that'll be what we'll focus on for the remainder of the 2 hours and 40 minutes. I'll pause if there are any questions. Now is a good time. I'll take a 30-second break and otherwise move to the next topic. So we started with this X-ray example I'd given, right? And we said, look, we can use X-rays to diagnose pneumonia, and this notion that it worked very well in 1 or 2 hospitals, and then it suddenly did really well, but poorly when we went to a different site. So the question is why? Why did that happen? So it's really important to understand the why in these scenarios in order to understand what can we do to fix it. So here's the example. Turns out in this example, the issue was that there were different scanning protocols being used. And because the scanning protocols were different, there was information here that tells you whether it's the front or the back of the chest. But in addition to the front and back of the chest, there was additional information around the type of scanner that was being used and the scanning protocol. And when you move from one hospital to another, the scanning protocols were a little bit different. And what it was doing was memorizing information in terms of the scanning protocol, and there was information leak in terms of the scanning protocol in the first couple of hospitals that helped boost performance. But when you move to the third site, because the protocols were totally different, that same information that was helping you in the first couple of hospitals hurt you in the later hospital. And so there are myriad examples of this where, if you're able to memorize something in the environment you're working in, perhaps you memorize some behavior, like, before this patient ends up getting this health condition, physicians actually often go ahead and write a note of this particular form. And then you use the fact that they wrote the note of this particular form to diagnose the patient. Well, that's not very helpful in practice because they wrote the note because they diagnosed the person. But your machine learning model doesn't know any better. So there are all sorts of ways in which there's leakage that happens. And that was the issue. So the question is, could this have been prevented? So given a data set, we learn a particular association between pneumonia and style protocols, and this doesn't generalize. And so the question is, what do we do? So can we just take that image and take a patch of that image where this information is, just take it out, and then, it's like a hack. I'll take the image, I take it out, and then maybe I just learn on that. That's actually pretty good. It would do better than the original solution. The only challenge is there is some useful information here we do need. So we do need this information about whether it's the front or the back of the image, but we don't need sort of all the other details. And so the question is, could we do any better? Same thing in the predictive policing example. As things change, another example of data set shift. So these are examples of data set shift where the question is, could we now learn models that would allow us to be robust to these kinds of scenarios? And that's the question we will answer. So these examples are different forms of shifts. Can we learn models that are stable to shifts? There's a large literature now in the last few years, especially on tackling shifts. And so we'll talk about what those are, some example ways to approach it. And today I'll start with sort of one example way to approach it. So historically in machine learning, when we saw scenarios like this, where we have one data set, we use the data set, we split it into train and test, we train using the train data, and then we evaluate performance on the test data. Great. And now when we think there's been a shift, that means we have a new data set that's a little different from the first data set. What do? Some form of transfer learning, which historically has been in the following form. Like I'm giving you on the right some examples, various different ways in which people have attempted it. But basically, you're going to use some samples from this target environment, and then you're going to retune your model to this target environment. And the retuning can be different forms of clever. So you can do importance weighting for covariate shifts, some kind of kernel matching approach. I mean, there are myriad such approaches, but all they're like intuitively, in a nutshell, what they're doing is I have data set one. Now, where I've learned my model, I have a new data set in a slightly new, different and perturbed environment. I'm going to use that somehow to retune my model. And one of the challenges that occur now is that it may be good at that second environment, but you don't really know, is it going to be good at the third environment? Is it going to be good at the fourth environment? The other thing is, if you're in a safety critical setting where making mistakes is very costly, like you could kill people, then this idea of like, waiting to be, you really be failure proofed ahead of time, which is you want to know what kinds of differences can occur and be proactively preventing failures against them, as opposed to after the fact, where you've collected a bunch of data and now you're seeing, oh, I've collected a bunch of data, I'm going to retune your model to that data, and now it's applicable on this new data, right? So in very fast changing environments, it's very difficult to apply this kind of technique where you're continuously waiting for new data to come in for you to be good on that data in order to be able to use in that environment at all together. So instead, we're going to do this notion of, so like I said, challenge here is you would need data from all possible test environments, which is very unrealistic to obtain. I kind of think intuitively of these methods as reactive. You kind of fix the errors once you already see them. And what we really want is some kind of guarantee up front, which is we want models that generalize to new unseen environments without needing to accrue massive amounts of data from them. And so shifting gears, that's sort of what this whole line of approach is about, which is data from target environments are not needed. We want to use alternative ways to specify desirable forms of robustness, and then use learning methods that can guarantee us that form of robustness. And so the benefits of this is obviously that performance of resulting models are less likely to deteriorate in unanticipated ways. They're more amenable to generalizing when we move from one environment to another. And it very much takes this failure prevention avoidance perspective, which is absolutely critical for safety critical applications. So with that in mind, I'm going to give you the overall, like, what will you learn from this 3-hour tutorial and the key bullet points you'll take away with after you listen to me and others talk to you today, tomorrow, and day after. And so first thing we'll start with is this question will help you answer, can we develop learning methods that are robust to shifts? That is, can we build these new classes of models that are called shift-stable models? We'll walk you through one example algorithm today. That's a shift-stable algorithm. We'll talk through how we learn it from data, talk about what kind of guarantees we give as an example, and turns out causality has a huge role to play in developing these kinds of algorithms. So we'll talk about that. Then we'll shift gears from, instead of talking about one algorithm and one end-to-end pipeline, we'll expand to start thinking about more broadly, how do we, like, what are the different classes of algorithms or approaches people are taking to develop reliable and robust models? And like, to what extent do these different types of approaches people are giving us, what kinds of guarantees are they giving us, right? Like, you have different classes of models. There's naturally a stability accuracy trade-off, where if you want models that are stable, in some scenarios, they're less accurate. There's obviously a stability accuracy optimal frontier, but different ways, different approaches are looking for different kinds of guarantees, like worst case performance versus average case performance. And so we'll overview this notion of stability accuracy trade-off. We'll talk about different approaches, and then we'll compare and contrast them in terms of what is it that they're prioritizing? What kind of guarantees are they prioritizing? And so by the end of it, you should come out of it with not just one algorithm, but somewhat of an overview of a landscape and different ways in which people are approaching it, but also where we think current gaps are in the field and where there's opportunity to develop new ideas. All right, I hope you're as jazzed to listen about this next place as I am. So let's start with one example of like a deep dive of a stable algorithm creating shift stable models. So in order to do this, here are kind of the 4 pieces to it. So the first piece is you want to go into a domain, you're going to start building a model, you're the expert, and you want to think about, well, what are the problematic shifts? Like in the pneumonia example, there was a shift, right? The policing example. So what are the problematic shifts that I'm worried about? It's like you're building a bridge. You want to think about what are the failure modes? Like, is there going to be a storm? Do you need to protect against that? Are there a lot of earthquakes? You need to protect against that. So depending on what your use case is, you're going to have a notion of what failure modes are both likely to occur, and it's important that we be robust to them. So that's the first piece, which is identify likely problematic shifts and specify which shifts to protect from. Then we go into describing a learning algorithm that once you specify it allows you to learn models that are robust to them, or will tell you such a model doesn't exist and you have to do some kind of trade-off. And then finally, we'll cover for this one example, what kind of optimality and soundness completeness guarantee do we get as a way to see one end-to-end. Okay, so for this particular example, I want to give you one practical empirical result, just to kind of, for those of you who are not super familiar with the literature, hopefully this motivates, and helps understanding like why should you care. So in this example, very, very simple, what we did was, these are 2 different classes of stable models. Like I said, there are many different learning algorithms that result in different classes of stable algorithms that, different varying degrees to which they are both accurate and stable. These are 2 algorithms that have the same kind of stability, but this happens to be more accurate than this one. And here in this case, on the y-axis, I'm showing you error, and I'm showing you measured error on a test set. So we trained it on one scenario, and now we're evaluating it in a test set. And we've, on the x-axis, varied the test set environment quite a bit. So we're taking the coefficients. So in this case, the model is super simple. We're trying to predict t. You have 2 input variables, a and c. And the part that's shifting here is the a variable. The distribution of a is changing across these different test environments. And what you see is when the train and test environments are very, very similar, the 3 models, this is sort of what you would do a naive regression model, like a classic supervised learning method without any notions of robustness, how this model performs versus the stable models perform. And what you see is like, as you would expect, this performs like classical learning performs really well when train and test environments are the same. And as you deviate away from these environments and you get, test environments that are very different from your training environments, if you go on either side, you can see performance now starts to deteriorate and errors start to increase. On the other hand, the thing that's interesting about the stable algorithms is, yes, they try 2 different of stability trade-off, stability accuracy trade-off, but the stable algorithms, the performance doesn't, you expect it to be invariant to this change in distribution, and it indeed is, right? So as the test environment changes, the model performance doesn't vary and behave in unanticipated ways or doesn't deteriorate. It's consistent as you would expect. Make sense? So that's a simulated data example. Here's the practical application of this in our diagnosis example that previously brought up. So here in this case, you have a graph of people placing orders of tests, lab tests and vitals, and we're using all that to diagnose. And this is a real practical data set. And as we saw differences in physician behavior and ordering patterns, this is an unstable model, 2 different types of stable models, but how their performance vary with these ordering patterns. And again, very, very scary if like your precision is varying so widely, with small changes in your data set. In this, to close this example, here what I'm showing is basically if the model was indeed stable, robust, and you could give guarantees that it was actually invariant to provider practice patterns, and it was invariant to the way physicians order, and that won't impact model performance within some reasonable bounds, then what we're seeing here is something really cool, which is a reliable learning method would actually put you in a scenario where you have 2 data sets here, regime A, regime B, 2 different regimes in which something was trained, a naive method trained in regime A. As the ordering pattern changes, we're showing a couple of different scores here. So what we're showing is, first thing is the prediction, the concordance between the prediction if a model was trained on regime B and tested on regime B versus trained on regime A and tested on regime B actually deteriorates. Like you would expect the models to be consistent, but it becomes inconsistent when it's naive. And the AUC, which is the performance, also deteriorates. On the other hand, if the model was trained in a way that it's expected to be robust to training ordering patterns, you actually see that not only is the performance across training in the 2 training and testing in the 2 regimes very consistent as you would expect, but also performance doesn't deteriorate. I went through this super high level, but just some practical examples and some pointers to papers, which you can go through again in your own time later. And, we'll dive into more technical details as we go through the rest of the tutorial. Okay, so now that we've seen a few examples, let's walk through an actual procedure for making this happen. So the first piece is we need to identify likely problematic shifts. Now, in order to identify likely problematic shifts, I'm going to use this example. Is it very noisy near me? Because there's some construction going on. Can you still hear me fine?
Yes, we hear you fine.
Okay, perfect. So in this example, first thing we have to do, the very first thing is, can we somehow start reasoning about what is the data, what are the variables in the data set, and can we represent it and start thinking about what shifts occur, right? So in this example, I'm going to take the sepsis example that I started with. So in this case, the variables are D is for demographics like age and gender. This is a simple graph. S is for whether or not you have the particular condition, sepsis or not. O is whether you're ordering a particular like lab or a particular vital sign. So in this case, it's just about whether I'm going to like vitals like blood pressure, heart rate are measured all the time, but certain lab tests like white blood cell count is only measured occasionally. So what O is saying is, am I going to order that variable? Am I going to order the test? And then if it's ordered, L tells you what the value of the test is. And then V tells you what the value of the vitals are. So to quickly summarize, in this example, you have a person, age, gender. Obviously, given your age, gender, your demographic, race, etc., it has an impact on your likelihood of having this disease. So that's what this arrow represents. Given whether I believe you have the disease or not and what your predisposition is, I may or may not choose to order the test. So this is what this O variable dependency is doing. And then once I order, depending on whether you have sepsis or not, what your predisposition is, I'm going to see your lab result. And then similarly, given whether you have sepsis or not and your predisposition, it's going to impact what your vitals look like, right? Very simple. It's not simple if you're not used to reasoning in graphical language. So fear not. Later, I give you a little take-home exercise related to it. But intuitively, conceptually, what it's allowing you to do is to reason about what are the variables in your graph, like what are the variables that you have data on, how do they relate to each other? And then most importantly, in red, which parts of the graph can be changing, or what parts of your domain can be changing over time. So in this example that I gave, turns out over time, this arrow that I've marked in red is what's shifting or changing. Like these stay the same, that's part of basic biology. But in this case, the guideline change when physicians choose to order certain tests. So in regime 1, they were ordering it very infrequently. In regime 2, they're ordering it very frequently. And so this is the variable, the dependency in your graph that's changing. And because that's changing, you really want to think about learning a model that's going to be robust to changes in this dependency. Okay. So what this graphical language does very nicely, it makes it possible to represent and reason about stable and unstable distribution and identify shifts we want to be able to robust to. So I'm going to push this idea a little bit further. So in this example, this is a case of smoking, not smoking, like in cancer, just to do a few such examples to get a sense for how graphs can be used to represent shifts. So I want to look at smoking habits now and predict whether you'll have cancer or not. And in 2 years, actually 2 years. And so effectively, this is the graph that says given today, I want to predict C at 2. And then let's say there was a smoking ban and now people's smoking habits are changing. Obviously, given or not they were smoking, is the prevalence of cancer changing? Well, that's biology. That hasn't changed. And so if we wanted to represent that information using this kind of a graph, what it's just saying is X is your input variable. You're trying to predict T, which is whether you have cancer or not, given X, which is your smoking habit. And the distribution T given X is stable, right? Like whether or not you're going to get cancer given you smoke, that's biology. That's not changing. On the other hand, X is changing because now that there was a smoking ban, the number of people who are smoking, that shifts. And who's choosing to smoke is shifting. Another example of what's called, so in the same example, we're going to use this notion of an S variable here. So in order to specify the unstable distribution, we basically take all the variables, like wherever there's a shift, and kind of use S to point at that shift or point at the distribution that is shifting. That was covariate shift, very common example here. There's label shift. So label shift is one where basically, rather than the distribution of X, the distribution of T is changing. And then going back to our pneumonia example, here you have a simple 4-part graph. T is your target diagnosis, whether you have pneumonia or not. D is the department where the image was taken. F is the style features on the scanner. And X is what was the image produced, right? So the lung X-ray image. And in this example, let's walk through it. What is stable and unstable? So given that you have pneumonia and given that you're using a particular scanner, we have a distribution of what the images look like, right? Because pneumonia shows up a certain way in a chest X-ray image. So this distribution is just biology, it's stable. We don't expect this to change in this example. It's possible, humans evolve, biology evolves, and it changes at the time scale of 100 years, but not in the particular scenario that we're interacting with. In this example, we've also assumed, given the department, these hospitals are very nearby, so the prevalence of pneumonia across them actually is pretty similar. So that doesn't change. On the other hand, as we identified, which scanner you use, and therefore the imaging protocols you use, do actually vary by department. So this particular arrow is changing. This part is unstable, these are stable. And so now that you have an image like this, you can say what was your goal was to try to figure out how to predict T, which is whether or not the patient has pneumonia, given X, and your goal is going to be, can I do T given X such that it actually doesn't learn any of this unstable information? So, using this language of graphs and selection diagrams, what it means is I'm going to take this graph. D in this case is, this is the graph like I showed you. In this case, let's even imagine D was missing and unobserved. It doesn't matter. But most importantly here, I've put an S variable, which is a selection variable that's pointing into F, because the distribution of F is changing given D, right? So this allows me to specify where is the shift happening, okay? And you can do this in very complicated graphs. If, we've done this in a lot of really, it's just a way to be able to have a conversation about your domain. Even if you don't actually end up using your graph in any formal way, just having some way to represent your data allows you to reason about this notion of shifts. What shifts can occur? What dependencies are in your data? And there's just virtually no way to guarantee robustness without being able to think about where the failure modes might be. So with that in mind, take home exercise. there are numerous tutorials on the internet on directed acyclic graphs. In fact, in machine learning, we spend almost a decade spending a lot of energy developing our understanding of graphs, learning graphs. You'll see other tutorials as part of SMILES that are all about structured learning of graphs from data. If you don't know the graph, you can learn the graph from data. We'll actually talk later about an example where we learn the graph from data automatically, and then we consume that graph in order to start reasoning about failure modes and shifts. But all in all, it'll be a very wise investment for you to go learn about DAGs and representing data using DAGs, and just do a couple of exercises of taking a domain and trying to think about it. So now let's imagine you have some graph. You were able to understand what are the things that would shift. Now we need to specify which shifts to protect from. So in the pneumonia example, we only have one big shift we are worried about in this case. We've decided we want to protect from it. That's it, simple. What this gives you is the ability to now talk to your domain experts and have this conversation, which is, there are 6 things that can change. Do we really need to worry about all of them? Because if you worry about all of them, as you will later learn, the more conservative you are, the more shift invariant you want to be, obviously your model, it turns out your model is also going to be less accurate, because there are things in the data it could learn, it could memorize, but it's choosing not to memorize so that it could be shift invariant. But that means then you're compromising on performance on this data set, right? So that's effectively the conversation you're having in terms of like which shifts you want to protect from. Now, it turns out, now that you have such a graph, you can actually obtain a resulting model that is like actually invariant to these shifts. So the form looks something like this, which is you get a graph, you identify which S variables here you want to control for, remove the ones you don't want to control for, and then this is an example algorithm. I'll talk about guarantees of this algorithm. For now, we'll call it the surgery estimator. What it does is, given the graph and given the invariant specs and which invariances you care to learn, what it outputs is a model that is robust to shifts in these variables you did specify you want to be invariant here. Okay, so what does the model output look like? So turns out the model output is of this following form. Effectively, it's intuitively taking this graph, it's learning a model which has implicitly the following form. Like it's a collection, it's taking this, and in graphical form, you can think of it as just learning parts of the distribution. So rather than learning the entire joint, it only learns parts of the graph. And the parts that it chooses to learn are the parts which have black edges, which means they are stable across data sets. And the parts that it wants to forget or not learn are the parts where there are red edges, right? It makes intuitive sense. If something isn't going to generalize, I don't want to learn it. If something is going to generalize, I want to learn it. And then in the so I'm giving you an intuitive description. That's not how the mathematics of it works, but intuitively, that's what it's doing. And the output of it looks like a collection of conditionals that are tied together in order to give the model output, because the conditionals are each learning parts of the graph that do generalize. And just for the purpose of completing this example, so it'll give you a model output, parts of the graph that do generalize, and then how you combine them in order to get your predictor. The learning method takes care of all that. And then from a fitting perspective, one natural question people have is, oh, if I do this, does that mean I can't use deep learning? Like I can't use DNNs or RNNs or my favorite model? Like, am I constrained in the choice of models I use because I'm, writing down these conditionals? And turns out you can just train, like you can use any of your favorite models in order to train these conditionals. So for instance, just like you would do model fitting in any other way, if T given A, B, C, D is temporal data with a lot of missingness, you might want to use an RNN for it. If A given C comma D is a logistic, then use a simple logistic link function. But effectively, the idea is to get this to a robust model, it's a collection of submodels that are stitched together, and the collection of individual submodels are each, you have the flexibility to train them as you'd like and use standard model selection procedures for evaluating quality. So that's sort of in a nutshell how the procedure would work. I'm actually going to give you Adarsh, in fact, is going to walk you through a little bit more detail. But before we do that, I just want to, for those of you who are curious on the how, but let me just finish it all the way through and talk through the guarantees first, which is, all right, let's trust we have this graph, we have the invariant spec, we have the learning algorithm. It's very flexible. It can learn and gives you some kind of robust output, like a stable model. What can I say about the quality of this model? Is it optimal? Is it just learning random stable parts of the graph, or is it learning the, is it as optimal as is it optimal and from an accuracy standpoint? What is it from a soundness completeness perspective? Like what happens? Can it always learn a stable algorithm? So let's go through that. So the first one, intuitively explained, is this idea that condition on the shifts you want to impose, right? So you basically said, I want it to be robust to certain kinds of shifts. Given that you want it to be robust to certain kinds of shifts, think of it as creating, this is not what's happening behind the hood, but intuitively. This is sort of how to think about it, which is intuitively, think of it as creating thousands of data sets where the variables that you said you wanted to be robust to, think of it as having an adversary. This adversary's job is to make you fail or lose. So what they're doing is taking the variables where you want it to be robust to those shifts. They're going to take those variables and make them randomly generate those variables to be as far away from the training distribution as possible. And they're generating them in a way to hurt you to the extent possible, right? So you as the learner, you want to learn a graph so that even if I had an adversary that tried to shift these distributions to whatever extent, I am going to still have a resulting model that whose performance is going to be invariant to those shifts, or is not going to deteriorate as shifts occur. And so the first result here is that basically it gives you this optimal stable predictor or optimal stable estimator in the class of all possible estimators, where you could arbitrarily shift these S variables we identified, and among the class of models that are going to be invariant to those arbitrary shifts, you're going to learn the model that is most performant. Okay, that was a bit of a handful, but intuitively what it says is, if you want to guarantee robustness, it's the most optimal thing you can learn in the class of models that guarantee robustness to arbitrary shifts to those S variables you specified. Okay, so that's good news. So that's now the question is, does it always work? So the procedure is sound, which is when it does give you an output, it does return you a model or an estimator. That estimator is indeed going to be invariant to anticipated shifts. However, there will be scenarios where it's going to give you an answer which is not possible. And in that case, you can also have this guarantee that the procedure is complete, which is if it fails, then no estimable invariant distribution exists. There isn't an alternative procedure that's going to get you there that has the same kind of guarantees. So that's good. It's both sound and complete. And then in the class, that's if it's possible to estimate, it gives you optimal. Now, one trick here is that in terms of practically applying these ideas, obviously, in order to be able to use this, there are certain good practices we'll have to adopt as machine learning model developers and researchers, which is first, you have to do things like understand the data, understand the domain, understand what the risks might be. Now, some people get very anxious because they say, well, this thing looks like it needs a graph. What if I don't know the graph with certainty? And turns out the graph that I used was a variant of a causal graph. And so they might say, well, what if I don't know the DAG? Aren't DAGs really hard to learn? Can I still use it? And so turns out you can, and we'll talk about some of this in our later sessions tomorrow and day after. Yeah, it's absolutely possible. Now, the other thing is, what if it turns out that what it returns to me says there isn't a stable distribution that's possible to build? Well, there are other forms of stability. At that point, what you can do is start to reason, well, do I need all of this? Maybe I can compromise in some places. Maybe I can impose different kinds of robustness, because what we tried to do was worst case, which is our adversary can arbitrarily move the distribution for the variables that we were worried about protecting shifts from. But there are other scenarios where instead of doing arbitrary, you could say, well, I want to be robust to a little ball around that. They can change the variable, but not arbitrarily, just a little bit. So can I deal with that scenario? And so those are some of the example things we'll talk about in the following session. So to recap, I covered why stability and understanding model robustness to shifts so important. Again, as I hope, as responsible developers, researchers, and practitioners, I hope I've convinced you that this is critical to care about with some of the examples we gave. We walked through an end-to-end example pipeline where we talked about what are the likely shifts in a domain, how do you specify these shifts, an example learning algorithm that gives you something that is robust. We talked about guarantees on this. And then, we'll continue this. But before I leave, I still have a couple minutes. So I did a lot of the presentation today. Adarsh is going to do more of the presentation for tomorrow. But Adarsh, do you want to walk through the mechanics of the surgery estimator for the people who are very curious about why it works in a couple of minutes?
Yeah, just to sort of peer a little bit under the hood of what's going on, and how you go from taking this graph and this data and outputting something that satisfies the guarantees that SUCHI was just talking about. So kind of to recall the setup for what's going on here. As an input, you're taking this graph where we have these pieces, these S variables that are telling us the shifts that we want to protect against, what we're worried about shifting. So this is a simple graph. We're predicting T, and the variables we're observing are X and F. And so what this graph is telling us, as far as an invariant specification goes, is it's telling us that we want to be invariant to the way in which F is generated. So this is like invariance to the style features that we were talking about in the example. So in terms of what the algorithm's actually doing, and so there are algorithms for doing this. We don't have to do this manually, but essentially what it's doing is it's using the graph and looking at the corresponding factorization of the joint distribution. And it's saying which of these pieces correspond to the shifts that we're worried about. So which of these pieces are unstable, these unstable factors which can vary and are affected by the shifts. And what we want to attempt to do is to delete these factors and retain the other factors which correspond to stable information about the distribution that we can use to predict. And so when you do so and you delete those factors, you end up with a distribution. So here at the top we have the factorization of the graph. When you delete that factor and simplify, you get the distribution below, which if you look has only these two factors where S is not involved in it. And so that means that these two factors are stable to the types of shifts that we specified we were worried about.
And others, just to make the tie to causality here very explicit, is effectively, this is almost like the resulting operator is like taking the original joint and then you're doing a do operation on these variables where you have S pointing to them. So in this case, it was like doing it's like a do operation on F.
So here we have already Susan on the room. So then we have to continue. Basically the next time, and I guess it's a good cliffhanger for we stayed. And I hope that the audience will be looking forward for our next session, because we already had a good introduction and now we're into the juicy details.
This sounds great. Well, thank you for having us, and see you tomorrow.
See you tomorrow.
Thanks.
See you tomorrow, Darsh. Have a nice day.
You too.